Welcome to our lecture Machine Learning, and today we want to talk about probabilistic inference. This is indeed a very fundamental topic, important for many of the following videos, so I would really recommend to follow this in detail and to read on in the other books, in the Murphy or in the Bishop book, if you feel uncomfortable with this. So we have already seen in the previous chapters that probability theory in general is a very important concept for machine learning. So we have seen, for example, the regions in decision trees, which have a distribution over the class labels, for example. But here we talk about a more detailed view. So I will give you an overview of the most important concept of probabilistic inference. And we start with a small experiment. So let's say you flip a coin 10 times, right? You have a coin, you do flip it, and what you observe is that, okay, it shows first head, then tail, head, and so on and so forth. So usually I'm asking here the audience, what do you believe, or what is the probability that the next coin flip shows a head or a tail? So think about it for a second. So there are many different choices, right? You could say, oh, it's 0% likely that we see a tail, or it's 30%, or it's 76% showing a tail. So I hope most of you will intuitively guess something around 30%, right? This number, for example. Why? Because in these 10 flips, you have seen 1, 2, 3 times a tail, so 3 out of 10 times you have seen a tail. So it might be reasonable to assume that if I flip the coin again with 30% likelihood, I'm getting a tail again. So this links a lot to what we have seen in these in a KNN or in a decision tree scenario where we said we have this number of regions, we count how often do we see class blue, red, or green, and then we set the probability to see or to assign this class if a new test instance arrives is according to these ratios, right? So 3 out of 10 times we see a tail, and with the other probability we see a head. So indeed, so intuitively, this is a good choice, 30%. But why is it the case? And this is what we want to study in the following more detail. And why is this one reasonable decision we can make among many other decisions we can make here? So the first point you should observe is that every flip is random, right? It's a random experiment. So technically speaking, this is like a Bernoulli distribution, right? So the outcome of this experiment, the coin flip, is 2 cases, head or tail, 0 or 1, right? So the sequence we're observing is a random sequence of outcomes, right? So we have random variables, and these random variables are technically speaking a Bernoulli distribution, so 0 or 1, and every outcome is either 0 or 1 with a certain probability. Okay? So here, this is more formally what I just said. So we have the probability that the ith outcome, right? So we have the outcome 1, 2, 3, up to 10 times, for example. So the probability that the outcome equals to tail equals to some specific probability. And the probability, of course, for head is 1 minus of this, right? It's the opposite because it has to sum up to 1 and we only have 2 outcomes, okay? And this is what we can write. So we can write this probability of showing tail, and I said it already, this is like a Bernoulli distribution with this parameter theta I, okay? So be carefully a bit. So the parameter of the Bernoulli distribution corresponds exactly to the probability of this outcome. This is different based on different distributions, right? You can have different scenarios. But here in a categorical setting, so where we have only 0 and 1, Bernoulli is the only choice. And then the parameter of this Bernoulli distribution is exactly the probability of observing this event, okay? And again, I'm saying this to make it very clear. Then, of course, the probability that the coin shows a head is, of course, then 1 minus this probability, okay? So this is our setting, and that we have here the same notation in the following videos and so on and so forth. We are usually writing it in such a way, okay? So we are saying F is distributed or drawn from a Bernoulli distribution with a parameter theta. Okay, so you can think about this notation really as that you do somehow like this coin flip, right? You are drawing your the outcome of this value according to a Bernoulli distribution, and Bernoulli is this binary experiment. Okay, So this is how we denote it. So note the index I here, and that's one important point we have to make. At the beginning, without any further assumptions, we have that every outcome can be a different distribution. So technically you have to think about just, we have multiple coins, so to say, right? And you flip every coin, right? And then every coin has its own distribution. Every coin might behave differently. Okay, and what we are trying to do here, and this was my question at the beginning, we are trying to reason about the 11th coin, so to say, or the parameter of the 11th coin. So what is the probability or the parameter of the Bernoulli distribution of these 11 coins? Because this will tell us how likely this coin will show head or tail, right? Because if we know that this is 30, then as it shows here, this is exactly then the probability that the coin will show tail, 30%, for example. Okay, so we're trying to reason about theta 11, technically speaking. And this is what we want to do now in a bit more formal sense, so to say, based on a solid foundation and not just based on this intuitive guessing. And we want to start with this concept of a maximum likelihood estimation, a maximum likelihood estimate, often abbreviated simply as MLE. Okay, so here's again our setting. So what did we do? We had this sequence of outcomes. Okay, this is our given data, so to say. Remember in supervised learning, right, we have given data, x's and y's. Here it's, first of all, much simpler, right? The data we have given is the sequence of outcomes of our experiment. And the sequence here was, for example, this head, tail, head, and so on and so forth, right? And what we want to reason about and what we are asking is the following question. We are asking the question is, what is the probability of seeing this sequence given the parameters of our distributions? Okay, since we had like here 10 different outcomes, we had 10 different Bernoulli distributions. So we have here theta 1 up to theta 10. Okay, so remember, and this might look confusing at the moment, we want to infer later on something about the 11th coin, right? The next coin flip. So at the first sight, there might not be any connection between these, right? And there's no hint how we can reason from here to here. But in a second, we see how we can do this based on essentially two assumptions we have to make, okay? So first of all, so what is this maximum likelihood estimate? The maximum likelihood estimate in general is that we want to find the realizations of these parameters. So what are the parameters here which are maximizing the likelihood? And the likelihood is exactly what we have here. The likelihood is, in a more abstract sense written, P of the data, often called X or D, let me call it D for data, given the parameter vector. So this could be a vector, for example. And the maximum likelihood estimate is the solution for these parameters which maximizes this function, the likelihood of seeing this data. This is what we want to do. Find the parameters which maximize the likelihood of seeing this data. Okay, so which parameters have most likely led to this data, so to say. Okay, good. So this is the concept of maximum likelihood estimate. And as you can imagine, this function here is called the likelihood function, and later on you see some other functions. But here this is the likelihood, which is data conditioned on the parameters, so to say. Okay, so again, how does this help to now reason about the 11th coin flip? And for this, first of all, we have to make a specific assumption. So here, that's the general form, right? We have this probability, the probability of seeing this sequence given the parameters. And first of all, what we assume is, and this is one common assumption, is we assume independence. We assume that every flip we have done is independent of the others. Every outcome we are observing is independent of the others. And what this means, and I guess this is what you have learned in your probability lectures, it means that we can factorize this distribution into a product of simpler functions. Specifically, we can factorize it in these independent terms. Right here we have the probability of the first coin showing head. Here we have the probability of the second coin showing tail. Here we have the probability of the 10th coins showing head, and so on and so forth. So simply speaking, independence means here this overall joint probability, and joint probability means that we have here jointly all observations together, right? This probability can be factorized in this product of individual contributions, okay? The product over all 10 outcomes probability that the ith coin shows its corresponding outcome, head or tail, given the corresponding parameter. Okay? So this is the first important concept. Independence assumption means that we can factorize this complex joint distribution into these individual terms. Okay? So now comes the second point. We can still not reason here about the 11th coin, right? Because here we have theta 1 up to theta 10, and there's no theta 11 even here, right? The point is, the coin is the same, right? Or all coins behave the same, right? If you take 10 different €1 coins, the 11th €1 coin is somehow the same, right? It has the same properties. So indeed, these theta i's are not theta 1 up to theta 10 or 11, but we can assume that they are all the same. All coins or coin flips behave the same. And this assumption is known as the identical assumption, so to say, or jointly together with the other assumption, this independence assumption. This is known as the so-called IID assumption. Independent and identically distributed. This is what we assume for our coin flip scenario. Meaning, technically, this product of these independent terms no longer means that if we have theta I, but we just have a single theta, right? Because every coin behaves the same. It's the same coin, or it's equivalent coins, so to say, right? We can say all follow the same Bernoulli distribution with the same parameter. So if the first outcome is a Bernoulli with 30% tail and 70% head, then also for the second one, 30% tail and 70% head, and so on and so forth. So the equation becomes even more simple now, right? Now this overall joint probability, P of the sequence, becomes really the product of all these identically independent distributed random variables, okay? So, right, so here, again, just that you read it correctly, here's the random variable, so the experiment we are doing, the ith coin flip, and this is then the outcome, so to say, or asking for the probability of this outcome. This is like the probability that the outcome of the ith coin flip is tail, for example, given that the parameter theta, and for the tail would be equal to theta. Okay? So now this allows us essentially to reason about the 11th coin flip, right? Because now we know that we don't have actually theta 1 up to theta 10, but we have just this single theta. And if we can now learn this theta from the given data, from these 10 previous observations, then we can also reason about the 11th observation, because theta 11 equals to theta as well, right? So this is the only hope here in this experiment, at least, that we can reason about the next coin flip, right? Using the 10 to learn something, right? We learn the theta from the previous 10, and then we can essentially assume that this theta also holds for the next one, and then we can make a prediction. Again, to a big picture here, let's say in the machine learning setting, right? This is also what we're doing in machine learning. We are training on the given historical data, and we learn some model, right? And this is often a probabilistic model, as we later on see. And this model, we hope that it also holds for the new data, right? So that this model does not change, that we can just, so to say, transfer it to the new data, that it has the same configuration, the same properties, right? So here it's the same. Good. But back to the coin flip. So in the coin flip, now we assume that this is our likelihood, our distribution, right? So remember, this function here is the likelihood function, data given the parameters. And now we assume that the likelihood function can be factorized in such a way. And this now makes it extremely simple indeed. So if you really want to write this down, right, you can see, okay, the first outcome was a head, right? And what is the probability of a head in a Bernoulli distribution? Actually, we had it. Let me scroll it back here. Right, we had written it here. Probability of head is 1 minus theta. Probability of tail is theta, right? So we can really say, okay, if we have a specific sequence, which could be head, tail, head, head, tail, head, 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 tail, head, we can just write down the likelihood, right? It's this term for head, this term for tail, this term for head, this term for tail, and so on and so forth. Meaning the overall outcome of this is simply theta to the power of 3, theta to the power of how many tails did I see, and 1 minus theta to the power of 7, the number of heads I've seen. Okay, so this here, this is the likelihood now of our distribution here, right? Given this sequence here, right? So given P of this sequence here, let's give it a name. Let's call this sequence S. The likelihood of the sequence S, given the parameter, is what we see here. Okay. So now we have computed the likelihood of our data in this somehow, let's call it parametric form, right? So if we would know this theta, right, we can write down our likelihood function and we can just compute it. Again, giving this IID assumption, independent, identically distributed data. So how does this now help? Now we have this nice analytical form of the likelihood function, and we could, for example, now plot this likelihood function. So here again, what we just computed is like this here, right? The probability of the data given the parameter. So we can think about as representing it as a function of theta itself. So how does this likelihood change when we are changing the parameter theta? Okay, and this is illustrated here. Okay, the parameter theta is of course between 0 and 1, right? It's like the probability of the coin showing tail. This can't be negative, this can't be larger than 1, so it has to live between 0 and 1 here somehow, right? This is the parameter of the Bernoulli distribution, and then we can plot it, or we can plot the likelihood with respect to this theta, right? Varying the theta, how does the likelihood change, right? And what you see is, for example, if we, let's say, pick theta equal to 1, which means we have a coin which always shows tail, right? Then, of course, this sequence has a likelihood of 0, right? Because it also shows head, right? So this sequence will never ever occur if we have a coin which always shows tail, right? So the likelihood is 0. Similar, if we have a coin which always shows head, this sequence has also a likelihood of 0, right? It cannot occur. But you see also, for example, if we have, let's say here, a coin which shows with 60% a tail, right? So a coin which is always like slight tendency for tails, right? Still, it's very, very low likelihood for the sequence, right? So if we have a coin which mainly shows tail, why should we get this sequence, right? Because it shows mainly head actually, right? So you see that different thetas lead to different likelihood. Right, again, this theta, a coin with 80% bias, very unlikely has led to this data. Or make it more specific, the data is very unlikely given this theta. This data is very unlikely given this theta. And now actually you see the main point. We want to find the maximum likelihood estimate. We want to find the theta which maximizes this function. So again, here's here the argmax. We are not interested actually in the likelihood itself. In this term, we are usually not interested in, but we're interested in the argument, the theta itself, which maximizes this function, okay? So the maximizer of this function, not the maximum itself, okay? So this here, this technically is the maximum likelihood estimate, the parameter which maximizes the likelihood. And as you see in this plot here, this, not surprisingly, and we see it in general, corresponds to 0.3. Number of tails divided by the overall number of observations we have. 0.3 leads to the highest likelihood. Okay, so this is the core idea of the maximum likelihood estimate. One important point I want to mention here, this function f theta, which we have plotted here, this is not a probability distribution. So you all know that probability distribution, if we integrate over the domain, they should integrate to 1, right? So here for probability distribution, this integral should be equal to 1. This here is not a probability distribution, okay? So this is just some function which measures the likelihood independency of this parameter, which in general is not a probability distribution, okay? So please don't confuse it. It's just some likelihood function, okay? Good. So as said, right, we want to maximize here this function, or we want to find the maximizer of this function. So how do we do this? This is more or less like high school math. You should all know about it, right? You could take the derivative of this function with respect to theta, you set it to 0 and you solve. You get the critical point. So technically you should have to check also whether this is a maximum or a minimum, as you know, right? Here it would be the maximum for sure. And then you have your solution, right? Take the gradient, set it to 0 and done. So the point is, here some small trick. you can always, or in many cases, apply. Actually, if you do this, it becomes quite messy, even for the simple function, right? So the function is indeed, as we have seen here, just this function, and taking the derivative and setting it to 0 it's not so nice, actually. So one common trick we are always, or in many cases actually doing in machine learning, is that we transform the function, and we specifically transform it by a monotonic function. For example, one specific monotonic function is the logarithm, right? So like, you know how it looks like. So it's a monotonic function, and the point is, monotonic functions, they don't change the critical points, they preserve the critical points, meaning what has been a maximum, or the maximizer to be specific, right? The maximizer before is still a maximizer after applying a monotonic function to it, okay? Monotonically increasing function if you want to preserve a maximizer to be a maximizer. And the logarithm is such a function, as said, right? It's a monotonically increasing function here, meaning that if we are interested in the argmax of a function f, we can equivalently look at the argmax of log of f, for example. Okay, so please remember this trick. This is usually applied in machining. We often reason about the log probabilities, for example, not the original probabilities. And this makes life much, much easier because, as you all, I guess, know, if you apply the logarithm to this function, this becomes rather easy because a product becomes a summation and exponent, they go in front. So simply speaking, you see it here. So this function here, which is like this product of terms with different exponents, if we apply the logarithm, it becomes 3 times log of theta plus 7 times log of 1 minus theta, right? So you see here this pluses, and you see that the exponent go in front. And this is indeed a much simpler function, okay? So now, taking with this function the derivative and looking for the critical points or the maximum, this is really much easier, and please do this as a homework. So try to take here the derivative and set it to 0, and try to derive here the derivative and set it to 0. You will figure out that this is much simpler, okay? So important, applying monotonic function preserve the critical points, so you can, you don't have to do this, you can equivalently do this. And you see it in the plot as well. You see here, for example, at 0.3, we have here reached the maximum. Okay, so this is the maximum likelihood estimate, 0.3 for the specific case. Can we do this for a general function, or general sequence, I mean, for of observations? Of course, we can do this, and not surprisingly, quite intuitively, the maximum likelihood estimate for an arbitrary sequence of these coins would be t, the number of tails, divided by the overall number of observations we have made. Okay, so it's really just this ratio. This is for the Bernoulli variables. This is the maximum likelihood estimate. Okay, so now let's go back to the actual question, right? Our actual question was the following, right? We wanted to predict what is the outcome of the next coin flip, of the 11th coin flip. And now we can do the following, right? We can simply say, okay, we know it's an IID scenario. We know the 11th coin behaves like the previous coins. And we have now derived that a good estimate for the previous coins is this theta MLE, so 0.3 in the previous case. So we can also say, okay, the 11th coin very likely will also behave like a Bernoulli distribution with the same parameter, 0.3. So meaning it shows tail with 0.3 probability and head with 0.7 probability. Okay, so it's again written down. Probability of the 11th coin was assumed now to be a Bernoulli with the same parameter, Ird assumption, which was just this probability, which is just this ratio. And now you can really justify formally why this choice, the 30% was good, which you make hopefully at the beginning. Okay. So does this maximum likelihood estimate now solve all problems? And as you can imagine, the answer is no. And I want to show you here, just for fun, some other sequence. So let's say I do a flip, I pick a coin, a €1 coin, I do a flip, I see head, I do another flip, I get a head. And what is now the maximum likelihood estimate? The maximum likelihood estimate would be 0, right? 0 probability to see the tail, right? It's tail, 0 divided by 2 is 0. So the maximum likelihood estimate would be 0. So if we now say, what is the third coin's outcome, right? So what do we expect as the next outcome? It will always say head. It will never say tail, right? But this is somehow unintuitive, right? Because we as humans, we know that a €1 coin, for example, is somehow like 50-50, right? It's expected that it shows the head and the tail, so the number and the what is on the other side, like the building, with the same probability, right? So roughly the same probability. So we have some kind of prior belief about a coin, right? And this maximum likelihood estimate is somehow violating this prior belief, right? So that the third coin will again show head, this is somehow not really what we would expect, right? So this is just potentially just happening by chance that we see 2 times the head, right? This is not too unrealistic anyways, right? So if you have a fair coin, for example, which is really 50-50, right? So then, of course, you have even a 0.25% chance of showing this result, right? So if you have a fair coin, in 25% of all cases, you see head and head, right? In the other case, you might see head and tail and head, or tail and tail, right? But this is not a very small probability. So what is going on? It's going on that this maximum likelihood estimate is again not take into account our prior knowledge how a coin should behave, right? So we, for example, know that coins usually don't always fail on heads, right? This is quite unrealistic for a coin. So we have some knowledge, we have some prior belief, and the question is, how can we represent such prior beliefs about a coin mathematically, and how can we then derive hopefully a better estimate about our parameter, about how the next coin will behave? How can we do this formally? And this is what we want to do with the next chapter, which we talk about Bayesian inference in general and specifically about maximum a posteriori estimates. Okay, so let's look at this. So the question was, how can we represent our prior beliefs mathematically in such a probabilistic framework? And the core idea of this Bayesian interpretation, which is quite subjective, right? That's a core idea actually here, is that we represent our prior beliefs by a so-called prior distribution. Okay, so this P of theta is called the prior distribution, and it represents what we think about this theta, so what we think about how a coin behaves, right? Remember, again, theta is how the coin behaves, like 70% tail, 30% head, right? And this is what we think about a coin before we have observed any data. So you see there is no data term involved, right? Before we had PD of P, the data given theta, this was our likelihood function. But crucially, here is no data. This is our belief about a coin without having done any experiment so far. Meaning before you have done these 10 draws, you have to make up your prior belief, your knowledge, so to say, about the coin. And this is indeed very crucial. So if we look at this prior distribution, it's very flexible actually, but it has to have this property for sure. It must not depend on the data you are later on taking into account, right? If you want to do these 10 coin flips, you have to make up your prior belief before that, so to say, okay? Other than that, it's just some arbitrary distribution over this corresponding domain, meaning it should be not negative, right, larger than 0, and it should integrate to 1. So it should be a proper continuous distribution, so a density function, right, a PDF. Okay. So these here are just usual properties of a distribution, right? And here it means a distribution over 0, 1, right? Because again, we have a coin flip which has between 0% tail probability to 100% tail probability. So this should hold on the valid domain, here on this domain. And this is really just crucial for the prior. It must not depend on the data, okay? But still, this is quite flexible, as I said, and this leaves us many, many choices we can pick here indeed. So we could, for example, say, here we have our theta, right? And we could say we don't have any knowledge about our theta, right? We say it's every theta is equally likely a priori, right? It's a prior. So before we've done our experiment, right? So I don't know anything about coins. I say it's flat. Any choice for theta is likely. Or we could say, which is potentially more realistic, I believe a priori coins are fair, right? Whatever coins we have, I expect they are mostly fair. Okay, in some cases they might be biased to one side or to the other side, but in many cases they are fair. You could also think about other settings, right? If you know that specific coins in specific countries are more like biased, then you could also do this, right? You could say, okay, I believe that coins mostly show heads. So it's more likely that they have 20% head likelihood, and then, of course, 80% the other one, right? So you could say this here, this is more what I'm expecting. Or like this, right? It's completely up to you. This is a very subjective choice. And this is baked into this Bayesian interpretation. You can pick this prior distribution however you want, right? And this is very crucial to know and to understand in general in machine learning. All these assumptions, like, for example, here the prior distribution, or also the assumption about how your machine learning model looks like you want to use a decision tree. These are all subjective assumptions you make. Of course, you can later on try to verify them based on some principles, but in general, these are subjective choices you make as a designer of these models. And here are these subjective choices. What do you believe about a coin without having done this experiment yet? Okay? Good. So how can we now use this? How can we use this kind of prior, right? That's the question. And now comes a very important formula you should all remember, which is the Bayes formula, which gives us the solution to the question, how can we merge together our likelihood, what we had so far, the data term, and the prior beliefs we have about our data. And here, this is what it's all about. So what we see here is, on the left-hand side, the so-called posterior distribution. Okay, the posterior distribution is asking something slightly different, but crucially different than the likelihood. So the posterior distribution is asking about what is the probability for a specific parameter given the data. So what do we believe about the parameter given the data? And this indeed incorporates two important factors, namely our likelihood, which was the likelihood of the data given a specific parameter, right? So knowing that the coin is 30% biased, what is the likelihood that I see this sequence I've seen so far, right? Times our prior belief, what we believe a priori about a coin, okay? And we have to divide this by the so-called evidence, which is usually a constant term, which encodes like a normalization, acts like a normalization constant to make sure that this becomes a proper probability distribution, okay? So one more time. So we have the likelihood term, which is what we have seen so far. The parameter is, so to say, fixed, and we check how likely is then the data given this parameter. We have our prior belief, very subjective choice here. And then by normalizing it, because you know, right, like a distribution should integrate to 1, right? The integral should be 1, or in a discrete case, all these histograms should sum up to 1, right? We have to normalize it. And this then leads to the so-called posterior distribution, okay? So this is really just Bayes' rule, so you can reformulate this distribution into the other one. Of course, what you could also see, you can also write it in the following way, which is sometimes easier to remember, like this, right? You can just apply standard mathematics. So theta given d times p times d equals to p times d given theta times p times theta, right? Which is equal to theta, the joint distribution. So this is what you might have learned in some standard probability lecture, right? So this here is known as a joint distribution, probability of theta and the data, right? So what is the probability of a specific theta and a specific sequence, for example? And this is the same as first reasoning about what is the probability of the data, and then given this data, the probability of theta, or in the other reformulation, probability of a theta, and then given this theta, probability of the data, okay? So this is potentially an easier way of remembering Bayes' rule. We have the joint distribution, which can be factorized in these two different terms. And once you have these two different terms, you can put this in the denominator and you end up here with this result. Okay? And this, again, what we see here is known as the posterior distribution, not the prior, but the posterior. So the distribution after we have observed the data, so to say, right? Posterior distribution, which is made up of these two terms again. Okay? So again, prior distribution before we have seen the data, posterior distribution after we have observed the data, so to say, right, which contains the likelihood and the prior. And usually we only talk about these terms, so we make it proportional only, right, because we ignore this normalization constant because it does not depend on the theta itself, right? So this is a constant. The data is given, the probability of the data, that's what it is. Here it is, right? So this is usually ignored, so we make it just proportional, okay? So again, this is very, very important to remember. Posterior is proportional to likelihood times prior. Okay, so this is actually what I said already, right? So usually we just care about these two terms. The evidence term, we in many cases are not interested in this at all, but if you want to compute it, you have to integrate, right? You have to integrate what I just said, so you can look at the joint distribution, for example, and you can integrate over the theta, so you should marginalize it out. This is how it's technically called, right? And so you're marginalizing out this parameter, and this leaves you with this variable, right? Because this is gone. This is in some cases hard to compute, or in many cases actually hard to compute, but in some cases we can do this. But as said, mostly we're not interested in this because here is no theta. We just care about finding solutions for this, right? This is what we wanted to figure out here. Okay, so now looking at this Bayes formula, it tells us how we can incorporate our prior beliefs in our decision, namely based on this simple product, right? Again, let's say we have some prior belief. Let's say we believe it's mostly fair coins we are assuming in the wild, right? It's an unlikely super bias. So let's say this is our prior. Let's say this is our likelihood. And this is what we have seen before, right? This is the likelihood function we have seen before, right? It's a function which has here the parameter and here the likelihood. And remember, this is not a probability distribution, right? This is a probability distribution. This is not a probability distribution, okay? And if we multiply these two, we get this function, for example, right? Prior times likelihood gives us this function. This is still not a posterior distribution. This is not a distribution because this was also not a distribution. This is often called then the so-called unnormalized prior, right? So like here, we compute this. This is the unnormalized prior. It's just proportional. So we can, to find the actual posterior distribution, we can normalize by the evidence. As said, usually we don't do this, but if we want to, we can do this. And then it looks like this, for example. Okay, just scaling it here differently. And then we get the posterior distribution. Okay. And what do you see now? We see now the following. While the likelihood, for example, has here its mode, right? So for example, it was the experiment where we have like 70%, for example. Our prior belief, however, was that coins are mainly fair, so 50%. We see that the posterior is somewhere in the middle. So here in this case, around 60%, okay? So we really have these two factors, likelihood, which says 70, prior, more like close to 50. So the posterior gives us a good trade-off between these two, so to say, okay? Of course, the prior could also match the likelihood, right? This is not forbidden, but again, this is without seeing the data, before seeing the data, and this is like what we get from the data, and this is then the combination of both, okay? Good. And what you could also expect, of course, is the more data we see, the more we should, so to say, trust in the data, right? So if we have a prior belief about a coin, 50% most of the time. But now we do some experiment, right? And we do 1 million times a coin flip and it always shows head and head and head. Then, of course, it's quite realistic that this is really a completely wrong coin, which always shows head, right? So the more data we see, the more we should trust the data, or the less important becomes our prior belief, okay? And this is indeed also what we are seeing. So let's say, for example, we observe 2 times head and 4 times tail. Okay, so here it's a slight bias to the tail. Let's look at this actually, right? So here again, let's say we have a specific prior, which is here this blue curve, right? So let's say this is here our prior. Here's our likelihood function, right? So here we have, what do we measure here? Actually, we measure here apparently, because it's 30, we are measuring here with respect to heads actually, right? So the probability for heads is smaller. So here, this is theta with respect to heads. So we see here the mode, right? And Small side note actually here. So here, just for visualization purposes, we already scaled up the likelihood because otherwise it would be too small, right? It would be somewhere here below. So we scaled it up just to make it more clear how it looks like. And then we have the posterior, which is like this function. And you see it's again somewhere in between these 2 points, right? But what happens if we get more data, right? So here it's 2 and 4, here it's 4 and 8, here it's 8 and 16, here's 16 and 32, right? You see that the proportions, they stay the same, but you see that the likelihood becomes stronger, so to say, simply speaking, which means that if we can look at the posterior is drifting towards the likelihood function, right? So here it's still quite in the middle between the prior and the likelihood, but here prior is on the far right, and here the likelihood and the posterior is rather similar, okay? Which is intuitive, right? The more data you see, the more you should trust in this, and at some point the posterior is very, very close to the actual likelihood, okay? So observing more data increases the confidence in this estimate we are getting. So meaning this solution becomes closer to the maximum likelihood estimate, right? Because the maximum likelihood estimate was always here. It's here, 0.3, here 0.3, here 0.3, and here 0.3. Just the other solution, which you don't know the name of yet, changes, okay? Let me actually tell you, because it comes in a couple of slides, but it's not like here sequent. So this solution is called the maximum a posteriori estimate, okay? This was the maximum likelihood estimate, the maximum of the likelihood function. This is the maximum of the posterior function. So it's a maximum a posteriori estimate, okay? That's this term, which changes here, becomes closer to the MLE solution. Okay, so one other point, what actually happens if we pick a prior where we have 0 for some particular theta? So let's say we pick a prior where we say, I'm 100% sure that, for example, the coin will never show, or it will never be a coin which has 80 or 100% tail probability. So what happens in this case? Think about it for a second. It actually means that since our posterior is a product between likelihood and prior, it will never happen that the posterior has any probability for these values. Meaning if you a priori say the value of 80 is not possible at all, even though if your data tells you 80% is the most likely solution, the outcome will always be 0 here because you're taking the product, okay? So if your prior belief is so strong, 100% sure it can never happen, then you can't change it in the posterior solution. Which also somehow means is it's always a good idea, if you're not really 100% sure, to have at least some epsilon probability for all these values, right? That you at least at some point allow the likelihood to dominate the decision, okay? So the posterior will always be 0 if your prior already tells you no chance at all. So please make sure that your prior is not too restrictive, not too hard, so to say. Okay, so now we come to the point of the maximum a posteriori estimate, which I actually already told you what it is about. So remember our original question, we wanted to reason about how the next coin will behave, or what is the outcome of the next coin, and for this we wanted to compute this theta value. Okay. As it turns out, this maximum likelihood estimate was actually really not the right question we were asking. It was actually really somehow like a weird phrasing, right? Because what we were actually asking here was, what is, given a specific theta, what is the likelihood of the data, right? Fixing theta, how likely is it to see this data, right? This is not really the question of what is the likelihood of this theta, right? What is the probability of seeing a specific theta? Right? It's a probability of the data given theta, but not the probability of theta, right? But indeed, what we have seen now in this posterior formulation, this is the right question, because here we are asking, what is the probability of theta given data, right? Please note this flip here. Again, here we are asking what is the probability of the data, so the likelihood of the data given a theta, and here we are asking what is the probability of the theta given the data, right? And this, of course, is more intuitive, more realistic, the correct question, because in practice, the data is given and we want to reason about theta, right? Not this surrogate proxy here, so to say, which flips the two different roles, okay? So indeed, technically we should care about, technically and actually intuitively actually, we should care about the posterior distribution, the probability of this parameter given the observed data, okay? So we shouldn't solve this optimization problem, we should solve this optimization problem. And this is what I've already shown you on the previous slides, right? So we should look at the maximum of the posterior distribution, which is called the so-called maximum a posteriori estimate, the maximum of the posterior distribution. Or let me be specific here again, the maximizer of the posterior distribution. So the argument which maximizes the posterior distribution. Okay, so here one more time, right? So what do we want? We want to solve this here. We want to solve we want to find the maximum of the posterior distribution, which can be reformulated based on Bayes' rule in this term, right? Likelihood posterior divided by the evidence term. As I said already, the evidence term we're usually not interested in, and here you see why. Because this evidence term does not contain the parameter theta at all. So here is no theta. And here's the second trick. If you want to maximize a function, right? You want to maximize a function. Actually, you want to find the maximizer again. So let's say you want to argmax some function f of some parameter theta, right? Of course, this is the same as the argmax of this function scaled by some constant, right? So here, this is the important point. Here's some constant which does not depend on theta. And this, of course, doesn't change the solution of the argument, right? We're just scaling up and down the function, but where the maximum is, right? Where the maximizer, at which position on the x-axis, so to say, it is, this doesn't change if we just multiply it by some constant. And this is indeed what's happening here, right? So this is some constant. I mean, it's division, but it's meaning 1 divided by some number. It's just multiplied by some constant. So this is really what we can just ignore, okay? So we can ignore this constant, which we multiply, right? So we essentially have to just solve this problem here. Again, this is a general trick you should remember. Constants you can ignore. So multiplying by some constant can be ignored if you're interested in the argument which maximizes this function, okay? So we want to maximize this term here, right? And how do we do this? I mean, we can just do it again analytically, right? If you know how this looks like, you can take the gradient, you can set it to 0, and you are done, okay? So how do we do this now, right? So as said, this here, this is what we derived already, right? This was our likelihood function, theta to the power of tail times 1 minus theta to the power of head, for example. But what is this? What is this here? So we said so far that this is very subjective, right? We can pick different choices, whatever function we're interested in. But as it turns out, there are some functions which make our life easier. And this is what we want to look at the following, because we usually want to have an easy life, right? And one way here in this case of this coin flip example, in this Bernoulli case, is that we say, let's pick the prior distribution to be a so-called beta distribution. You see in a few slides some illustration of what this means. So formally, the beta distribution is parameterized by this. It has two parameters, a and b. And important to remember, this is a distribution over theta, right? This is not a distribution over our data, right? Before, we had something like the coin f, that was our coin fi, is following a Bernoulli distribution with respect to a parameter theta, okay? Bernoulli distribution means the outcome is 0 or 1, and the theta tells you with which probability you see the 1, okay? So this is what we had before. This is the distribution over the data, okay? Here, we have the distribution over the parameter theta, okay? So you could equivalently write it like theta is distributed like a beta distribution with the parameters a and b. Okay, so please, that's very crucial, note the difference here. The data f is distributed according to a Bernoulli. The parameter theta is distributed according to a beta. Okay, so in the following lectures, you will also learn about probabilistic graphical models, and we will have some introduction video to this as well. But you can also illustrate it like this here. Essentially you have here your theta, which somehow depends on A and B. Oops. Let me draw it somewhere else. So you have your A and B, and they are responsible for finding the theta, and this theta is responsible for F. And since you have multiple F's, you draw these boxes and you have n many of these. And this is what you will learn later in some videos. This is known as a graphical model, probabilistic graphical models. So you have here your values of A, B, which influence your theta, right? Theta is a beta distribution based on these two parameters. And then your data, you have n many observations, n many coin flips. All of these, they depend on theta. Okay? So this is like the illustrative view. And please be careful what are the distributions of these random variables. So this is distributed according to a Bernoulli, 0, 1. This is distributed according to a beta distribution. Okay? So here the formal definition, and not talking about the formal definition because that's not too insightful. Let's look at some plots. So what can we do with this beta distribution? So we can, for example, parameterize it in such a way that A and B are equal to 1, so A and B 1, and then we get this flat curve, right? We see that the probability that theta is 0 or 1, this is constant, so everyone is equally likely. Of course, negative values are 0, not likely at all, so 0. And values larger than 1 are also 0, likely, right? So it's living on the space between 0 and 1. But here it's flat. So this essentially tells you, I have no clue about my cons, right? Every bias is equally likely. And then you can do different stuff, right? You can make, for example, beta 2, 3, right? Then you have here like this small tilt to the left-hand side. You can pick beta 8, 4. So now the first one is larger, then it tilts to the other side and even to a stronger degree because the numbers are getting larger. And you can also get some weird behavior where you make these numbers smaller than 1. So 0.7, 0.1. Then it's, for example, symmetric, but it's tilting to the outside, which means if I have a coin, I either believe it's either biased to one side or it's biased to the other side, but I'm very sure it's never a fair coin. Okay, so this is essentially the opposite of a realistic coin. It's either on one side or on the other side. So you believe in cheating coins only, so to say. Okay, but you see that this beta distribution is already quite flexible, right? It has no information, different biases. It can also be, of course, like completely fair in the middle, but also this weird behavior. So it's quite flexible. So let's pick this beta, right? Let's do this because it sounds nice. And now, how does it all play together? Let's just plug it in and let's see, okay? So here we have our posterior we are interested in, likelihood term, prior evidence we can ignore, right? And now we just plug in our values. The likelihood we have seen before, right? That was our simple function. We have seen just plugging in this Bernoulli distribution, right? Theta or 1 minus theta. And then we had our beta distribution right here, our prior, which is this term, okay? So by the way, why we're using this here? Because these terms, these can be thought about as like, again, hyperparameters. We don't want to learn something about these. These are usually fixed, right? This is why we often ignore them actually, so in the notation. So this is what we have. And what do we have to do for the posterior? We just have to multiply it, as you have seen in the previous slide, right? Likelihood times our prior distribution. And now comes some surprising result. The nice result is, since we have picked this beta distribution, we can see that we can now nicely simplify this, right? Because you see that the beta distribution also has these two terms, which we have also seen here in the likelihood, right? And this term does not depend on theta. So what we have learned before is, right, so here, this is constant, this is a constant, so we don't care about it, right? Because we just care about later on about the maximizer, the proportional sign, right? So this and this is proportional by just getting rid of the constant, right? We can ignore all multipliers which are constants, okay? That's first point. And second point is we can, of course, merge these together because both are theta to the power of something or 1 minus theta to the power of something. So overall, this simply becomes theta to the power of t plus a minus 1 and the other term h plus b minus 1, right? So this goes here and this goes here, right? So this is nice, right? We have now a very simple form. And actually now we don't have to do some crazy mathematics. So if we want to find the maximizer of this function, you should already know the solution, right? Because you know what the maximizer of this function was, right? This was t divided by t plus h, right? This divided by the sum of these two. So you can just guess now what is the maximizer of this function. Of course, it's this term divided by this term plus this term, right? So that was very easy. And this indeed now gives us the maximum a posteriori estimate. So here we see it one more time in detail, but I guess you can all follow this discussion based on the MLE estimate. So as before, we can find the solution very, very easy. Now it's just slightly different because we have slightly different exponents. And this gives us the maximum a posteriori estimate. Here already you see that this maximum a posteriori estimate is a trade-off, so to say, between the prior and the likelihood, right? Because this term was from the likelihood and this term was from the prior, right? The prior was configured by A and B. Quickly going back here, right? The prior was configured by A and B, these terms here. And you see that this includes both the data term and the prior term. The data term and the prior term. What you also immediately see is the more data I'm getting, so the larger here and the larger here these terms, the more dominating is this factor, right? At some point the prior doesn't play a role. However, if you have only few data, this is rather smallish and this might dominate your final decision, or at least has some effect on the decision, right? So here just very formally you see how this prior and likelihood terms play together, so to say. Okay, so now what we did is we computed first of all the maximum likelihood estimate, and now we also can compute the maximum a posteriori estimate. As it turns out, indeed, we can go one step further even, right? So we don't have to stop here, right? So is it really the best case to now really compute this? I mean, it seems to be better than the MLE, but is it the best? So potentially we're also interested in some other questions like, what is the probability that our theta lies in a specific interval, let's say? Right, so far we only get here a single number, right? Theta map is 0.656. Is it really so interesting? Might be more interesting to say, okay, is it likely between 0.7 and 0.8, for example? And indeed, we can do this by looking at the entire posterior distribution, right? Remember, so we looked at this posterior distribution, which we got from the base rule, and at the end, we only looked at this map estimate. But why not looking at the full entire posterior distribution? And indeed, as it turns out, in some cases we can easily do this. So what did we do here? So far we have derived the posterior distribution only up to the normalization constant, meaning we looked only here at the proportionate term, which was this nice and simple function. So the point is, since this is only proportional, right, this on the right hand side is not a probability distribution yet, right? So what was the condition? It has to integrate to 1, right? So we can find this normalization constant by finding this solution by integrating it essentially up to 1, okay? So technically what we have to do then is, okay, we take this term, we compute this integral, right? So from 0 to 1, because that was a valid domain. This might give us some number. Let's say the number is 20, right, or whatever number. And then if we multiply this term here with 1 divided by 20, then this would be our final probability distribution, right? Because then this full term would of course integrate to 1. This integrates to 20, this 1 divided by 20, so it would integrate to 20, and then the final solution here would be our posterior distribution. So this is usually not nice, right? Because no one really likes computing integrals, and indeed in some cases it's really not analytically possible, and then we have to do some approximation, numerical calculation. This is really not nice, and it's super expensive. Okay, so this brute force calculation is very likely not the way to go. I want to quickly show you here a second trick, which is extremely crucial in many parts of, let's say, machine learning, probabilistic machine learning. We can do it by pattern matching, okay? And indeed, as it turns out, you have seen already the solution of this posterior distribution, right? So remember that we defined the beta distribution. Before we called it beta distribution A, B, right? So our prior was a beta distribution. What again was the shape of a beta distribution? It looked like this. Now we're using on purpose alpha and beta, right? So it had here some term, right? These gamma terms, and then we had the theta to the exponent and 1 minus theta to another exponent, right? So this is a beta distribution. can we use this somehow, right? Can we use this result of a beta distribution, link it somehow to this here? And of course we can, right? You just see that this is essentially a beta distribution where just the normalization constant is missing, right? Put differently, here we have some alpha minus 1. Wait a second, we could call this here alpha minus 1, right? Here's some beta minus 1. Wait a second, let's call this beta minus 1, right? Or put differently, right? We can say beta equals to h plus b and alpha equals to t plus a. Here the cardinality sign. So we see that if we instantiate alpha with this term and beta with this term, this here exactly becomes this here. And accordingly, we know what the normalization constant is, which is missing, namely the gamma function as defined here, right? Because now we have the alpha, we have the beta. So here, this is the normalization constant we were missing. And we don't have to calculate some complicated integral. And this is indeed what is just shown here on the slide, right? So we see that the beta distribution and the unnormalized prior, they match together, and we can now just plug in our normalization term, right? This here was t plus alpha at a, this here is h plus b, and then we get our nice normalization constant. Or put differently, the posterior distribution is simply a beta distribution again with these two parameters, right? So here, remember that the parameters are always without the minus 1. So the posterior distribution is just another beta distribution. Okay. So 2 points. Always remember this trick. Try to match unnormalized distributions to known distributions. Right. So you see here the match, right? And then you get the normalization constant for free in many, many cases. Okay. Second point I want to mention here is you see now that the posterior distribution is also a beta distribution. So the prior was a beta distribution, and now also the posterior distribution is beta, just with slightly different parameters. And in these parameters, you again see how the likelihood plays a role, right? So in the prior, it was really just beta of A and B. And now in the posterior, we're adding the observations, right? We're adding how many tails we have seen and how many heads we have seen. And this then gives us our final posterior. We see how these two terms, prior and likelihood, play together. Okay. So the posterior is a beta distribution, and you know how these shapes look like. You can just plot it. Okay, this was nice, right? This was nice. It was just a beta. Everything was flowing together. We had the likelihood which was a Bernoulli. We had the prior, which was like a beta. And then luckily, the posterior was also like a beta distribution. Were we really just lucky here? And the answer is indeed not really, because there's a concept of so-called conjugate priors. And this is what we used here. A conjugate prior, more formally, is a prior distribution to a corresponding likelihood, such that the posterior has the same form. Okay, this sounded potentially confusing. So let's say you have here the posterior, which is proportional to the likelihood times the prior. So what is a conjugate prior? It's a prior, let's say a beta distribution, which together with a corresponding likelihood, the Bernoulli, leads to a posterior which has the same shape. So this distribution and this distribution are both beta distributions, for example. Okay, it's conjugate to a specific other likelihood distribution, right? So here, for example, if this is Bernoulli and we pick here beta, then this is also beta. If this, for example, is a Gaussian and we pick here a Gaussian, then this also becomes a Gaussian. If this is an exponential distribution, there's something else which is then here the same. Okay, so not for every distribution we have this, right? Not for every likelihood function we have a conjugate prior, but for many likelihood functions, right? Gaussian, Bernoulli, and so on and so forth. For many likelihood functions, we have a so-called conjugate prior, and then it's strongly recommended to pick this conjugate prior because then you already know that the posterior is the same, is from the same family, right? Beta and beta. Okay, this makes life much easier because you already know how this has to look like. In general, just as a remark. If this is some complicated function, we don't have it, and then we also don't know how this looks like. So in general, these here might not be the same, right? This could be distribution type A, distribution type B, and this could be completely different distribution, okay? But in this case, in this conjugate setting, everything is usually nice and it nicely flows together. And this is what we have seen here for this coin flip. Okay, so as said, right, this is what we already discussed orally, right? We can interpret these parameters A, B as our prior beliefs, and now for the posterior, we're just adding our observations, and then we get our final belief, so to say. Okay, so what is the advantage of this? Now we have this full distribution, which of course gives us much more information, right? So we can say now, for example, the posterior distribution looks like this. Be careful here, right? So we had here, for example, our prior was, for example, 1, 1, flat, no information. And then we had, for example, observed 3 tail and 7 heads, right? And we are getting this kind of posterior distribution, okay? So again, why is 1, 1 no prior essentially? Because remember, the beta distribution for 1, 1 was really just a flat constant, right? And of course, if the prior is a flat function, so it's a constant essentially, like let's say it's always 1 or always 5, as we know, this doesn't play a role because we're anyway talking just about proportional, right? If this is always a constant, then the likelihood equals to the posterior, okay? Flat prior means likelihood equals to posterior, at least on like bounded domains. Okay, so what is then the advantage of this, right? Of course, we have a nice picture, right? We can look at it and we get more information, but we can really now ask different questions. We can ask the question, for example, what is the mode of the posterior distribution? Here, for example. Oh, this is actually what we did already know, right? This is our maximum a posteriori estimate. The mode of the posterior distribution. But we are not restricted to the mode, right? We could use, for example, also the expected value, which is often actually a better estimate, right? Because this is the most natural question to ask. What is the expected theta, right? We do a coin flip and we are asking, what theta do we expect? Okay, so the expectation of this, so truly speaking, the mean, so to say, right? Which might not be here, it might be at some different position. It could be, for example, here, depending how the distribution looks like, right? So the mode and the mean, they might not coincide, and usually they don't if it, for example, is not a symmetric function. So here, for example, the mean, or the expected value, might be a bit to the right-hand side, okay? Just gives you a better estimate, for example, a more natural estimate even, right? The expected value. But you could also look at the variance, for example, right? So how much is this estimate fluctuating, so to say, right? Is it very stable, right? Is it really very sure that it's this estimate, right? Are you very sure that the coin is like 0.7? Or is it a very high variance, right? Like here, for example, this could be wiggle around a lot, right? So you're not really sure where this theta is. It could be somewhere here in this range. So it's quite a large region. And indeed, this is also what you can just compute. You can find credible intervals. For example, you could ask the question, what is the probability that our true theta, right, the behavior of the coin, is between 0.2 and 0.4, for example, right? So what is the probability that my coin has a behavior somewhere here in this region? So you have to integrate this region here then, right? This is what you could ask. So for example, you could say 95%. Then you are very sure that your theta is in this interval, for example. So you can really ask more than just having this single point. So indeed, these estimates, this theta map and the theta MLE, they are called point estimates because we just get a single point for our parameter, a single guess, so to say, about our parameter, a single estimate. In contrast to this here we have this full distribution, right? Full distribution versus a point estimate, okay? So by the way, one last comment, which is here on the slide, please don't confuse this here with like these confidence intervals you see in like frequentist point of view. These are two very different principles. One is this Bayesian view, one is the frequentist point of view, just as a side note for people who are familiar with confidence intervals. Okay, so long story short, the posterior distribution really gives you more information. It's much more helpful. If you can compute it, go for it. In many cases, actually, however, you can't compute it. And then, of course, you can go with these point estimates. Okay, so here just a quick wrap up on what we just learned. So we learned 3 different ways to estimate parameters, right? To learn something about your coin, so to say. You have your data, you have your prior belief, and you want to learn something about your coin. How does this coin behave, so that you can, for example, also predict how the next outcome will look like, okay? And we use these 3 ideas: maximum likelihood estimate, which maximizes the likelihood function. It's a point estimate, and that's the solution. The maximum a posteriori estimate takes into account the prior belief. We're maximizing the posterior distribution. That's the solution. And last but not least, we can look at the full distribution, which here in this case was also just the beta distribution, if the prior is a beta distribution, which had this nice form. So all these have simple forms in a conflict example. Okay. And this is also what we have seen already a couple of times now. So we can, for example, now link together these different properties. So what I said already is that the mode of the posterior distribution is really just the map estimate, right? Because the mode is the maximum of this function. And if you open, for example, any textbook, right, and you see what is the mode of a beta distribution, it will tell you that it looks like this here. And this is actually another benefit of deriving the full posterior distribution. If you, for example, derive that your posterior distribution is, let's say, a Gaussian, you know that the mode of a Gaussian is the mean itself. You don't have to maximize the function, right? So how did we find this map before we computed the gradient, set it to 0 and solve, right? You don't have to do this if you know that your posterior distribution is a beta. And if you open textbook and you see, okay, the mode is like this minus 1 divided by this plus this minus 2, right here, so this here, then you don't have to calculate it. You don't have to calculate the gradient. You don't have to set it to 0 because you can just look at the mode, okay? That's one point. And the other point is what I already said is if we pick a flat prior, meaning A equal to B equal to 1, sorry. So this is 1 and this is 1. And then you look at the mode, then you get the maximum likelihood estimate, right? And again, then it just gives you the solution, right? So again, open the textbook for beta distribution, tells you the mode, make this equal to 1, and you are done, okay? So you don't have to compute derivatives. You don't actually have to maximize at all. So mode is a map, and if the prior is flat, the mode becomes the MLE, okay? Good. So there's another question now to ask, of course. Now we have derived all these different estimates, but the follow-up question is, of course, is how many coin flips do we need to be very confident, to be very sure about our estimates? And this is also what the posterior distribution now allows you to evaluate, so to say, right? Because you can, for example, just visualize the posterior. So here, for example, you see if you have only done a few coin flips, the posterior is still quite broad, right? You have this large variance. If you increase the number of coin flips, you see that the posterior is becoming more peaky, right? So the posterior distribution can give you a feeling already, how sure are you about your estimate? Do you have to do more experiments, more coin flips to make it more peaky, or are you already satisfied, right? Because here it's already quite close by, so you can be very certain that it's 0.2, while here you are not too certain, okay? That's another advantage of the posterior, because you can get a better overall picture. So how many coin flips you have to do. Just quickly, another perspective, which is often used for such setting, quickly the frequentist point of view. So, so far we have derived here this maximum likelihood estimate, right, which was a simple equation. And again, we can ask the question, how many coin flips we have to do, right? It's 1/4 enough, or it's 10/40 better, right? So what can we do? So in this frequentist point of view, we rarely talk about these subjective priors, right? But we can do something else. So if we can, for example, use a specific concentration bounds, or here we can use a so-called Hefting Inequality. So it's a Hefting Inequality, again, just open a standard textbook. Here instantiated to our setting, it tells you the probability that the maximum likelihood estimate, which we derived, differs from the true theta, right? The true theta is the one we actually never really know, right? Because we don't really know how this coin, for example, might behave, right? But the Hefting Inequality tells you what is the probability that the maximum likelihood estimate deviates from the true value by more than epsilon? So this essentially says that our estimate is off, that it's too far away, right? So here this tells you that the estimate is too far away from the true value. Okay. The Hefting inequality tells you that the probability that we are too far away is smaller than some specific term here. Okay. So some epsilon, which is here this, and then n is the number of flips we have done so far, the number of coins we have flipped. Okay. So this gives you some bound. Okay. So we know that we have to do a specific number of coin flips to be sure that the probability that we are off is only small. Or put differently, let's say we want to be sure, and here we have written it, so we want to make sure that we are 0.01, at most 0.01 off. Okay, so remember, this is the probability of being off, far away from the true value. Okay, and we want to make sure that the probability of being far away from the value is smaller than 0.1. Or put differently, the probability that we are close by the true value is at least 0.99, right? So having this value, we can just now solve for n, okay? And giving a specific error tolerance, right? So let's say here in this example, we want to be 0.1 off at most, right? So this should be 0.1. So we want to be 0.1 off at most with a specific probability. Now you can solve for this, right? So you see you have here 0.1. You have 0.01, sorry. This is your error, your tolerance, the probability you want to be sure about. This is your error you want to accept, 0.1. N is the number of flips you have to do. And then you can just solve it, right? So here, this is an inequality, right? And you have epsilon given, you have delta given, you want to solve for n. So how many coin flips you have to do such that this equality holds, okay? And in this case, it turns out this is roughly 265, for example, for this error tolerance. Again, only be careful with the sign, with the order here, right? Again, this asks for being off, being far away, and it's the probability that this is far away is smaller than this. And usually you phrase it then the other way around. The probability of being closer than 0.1 by should be larger than some number, okay? So if you want to phrase it intuitively, this really says with very high probability, I'm close to the true estimate, right? With very high probability, I'm at most 0.1 off from the true estimate. And to achieve this, we need 265 samples. Okay? So that's another way of estimating this, which is a very different principle than doing this posterior visualization. Okay, so again, to quickly wrap up, so we have now learned what is a map, what is an MLE, what is a full posterior distribution, how to derive this. You learned a few tricks, how to make it faster, not so tedious. And you also learned how you can estimate how many flips you need to be sure about your result. You can use a Bayesian view, looking at the posterior, or you can use a frequentist view using some kind of Hefting inequality, for example. So finally, let's go now back to the actual task we wanted to do, which is about predicting the next flip. But before we start on that, let's take a short break. Okay, welcome back. So in the last part, we really want to answer the final questions we actually were interested in, namely predicting what will be the outcome of the next coin flip, right? So we have seen two versions so far, right? We can use the MLE or the map estimate. In both cases, we got some kind of point estimate. And then for predicting the next coin flip, we can just exploit this Ird assumption saying that the next coin, so the 11th coin flip, will behave the same. Meaning the 11th coin is also just a Bernoulli distribution with the MLE estimate or with the map estimate, right? Or put differently, then also the probability that the next coin shows tail is either theta MLE or theta map, okay? So that's what we could assume, and that's what we can do. That's one way of doing it, and potentially also the default way of doing it, specifically for more complicated models. However, in general, we might also have the entire posterior distribution available as we just have derived. And in this case, we can do a more advanced, more principled analysis indeed. Because as it turns out, we are really not interested in these thetas, right? The thetas here, they were just really a means to answer the question, what will be the next coin flip? It's not, or often not really interesting to talk about the theta itself. Actually, it depends, I would say, right? In some cases, the theta might give us some knowledge, right? So for example, how this coin really behaves and we want to use it. But if we are just interested about the prediction for the next coin, then the theta itself is not really interesting, right? So who cares about how the theta looks like if your goal is to predict stuff? It's a bit like in a machine learning setting in general, right? So if you want to use a decision tree just for predicting what the class of an image or whatever feature will be, then you're not really interested in the parameters of the decision tree, but we are just interested in what is the prediction. On the other hand, right, if you want to care about interpretation, then of course the parameters itself might be important. Okay, so here we have the parameters and of course then we can interpret it. But back to the actual point. So what is if we have the full entire posterior distribution? Can we do better? And the answer is yes, because technically we are not, as I said, interested in the theta, but we are interested in the following question, right? So what is the probability that the next coin, so here we should actually have an 11, for example, the next coin shows tail, given the data and given our prior beliefs parameterized by A and B of the beta distribution. So this is what we have given. We don't have the theta given. We don't want to derive the theta, but we want to answer this question. Okay? And this distribution indeed is called the posterior predictive distribution. So the prediction for our next instance, let's say, for example, given the data and given our other kind of hyperparameters we have attended. Okay? So you can really think about it like we are getting a new image and we take the historical data we have, we take the new image and we take some other prior knowledge and we want to predict for this image the class. This is called the posterior predictive distribution. Please don't confuse this with the posterior distribution you have seen so far, which was the posterior distribution over the parameters. What I'm always saying is, when you talk about these distributions, don't actually call it just posterior or likelihood or prior. Link it to the parameter you are talking about. Okay, so here it's actually the posterior over the parameters. Here it's the posterior over the outcome of the prediction, right? And then it's often called, this is why it's called posterior predictive, right? It's the posterior distribution over the prediction. Okay, here it's a posterior distribution over the theta. You can have a likelihood over specific variables and a prior over specific variables, right? So in the best case, think about what is the domain, what is the parameter you are talking about, right? Posterior over theta, posterior over x, posterior over whatever, okay? So that's very important to distinguish. But this term here again is called the posterior predictive distribution. And this is actually what we are really interested in, right? Making the prediction for the next instance. So how can we get this term? Indeed, we can just get it by some, I would say, rather boring mathematical derivation. So let's do this quickly and please check out the details in the slides later. So as a shortcut to make it a bit simpler, we call it now the outcome not tails and head, but we call it 0 and 1, which make the notation a bit simpler. So the question we are asking here is, what is the probability that the outcome is 0 or 1, given our data and the hyperparameters, okay? And as said, we can just do this by some boring mathematical manipulation. So if we look at this distribution here, we can, on one hand, inject, so to say, the parameter theta, right? We inject it here, but we immediately marginalize it out. So that's a standard trick in probability, right? You can always type like P of A. This is, of course, the same as integrating over B, and then you have P of A and B, right? So in the discrete setting, if you don't have an integral, but if you're more familiar with like discrete domains, you would have here a sum, right? So say you have different categories. So you essentially just sum up over all different outcomes, and then essentially this B disappears again, right? You inject it and you marginalize it out, so it disappears again. So this is equivalent, okay? So why does it help? Now you can apply another trick, which I have shown you already in the base rule. So here, this is a joint distribution over F and theta. You can equivalently write it as F and theta and the condition, and here's theta. Okay, so this condition stays, of course, right? But theta goes into here in the front, and here it goes in the condition, and that's of course also the same. It's just reformulating the joint distribution. So again, standard mathematics. And now comes the only interesting part, so to say. So we can simplify from here to this term, meaning this here can be removed from this term. Why is this the case? The point is, once we know what theta is, let's say theta is 0.3, right? We know how the coin behaves. Then the data and our other probability is no longer important because we already have figured out what the theta is. So technically speaking, we have some conditional independence assumption. Knowing theta, this f is independent of the data, right? So knowing how the coin behaves, we can already predict the next outcome. We don't need our probabilities and we don't need the data anymore, okay? So that's what this conditional independence assumption means. So here it's again written in some words. If we know the theta, the next the next outcome is independent of the previous outcomes, right? Because we already have the full knowledge which we need, okay? So as it turns out, right, so this posterior predictive distribution can be written in such a way. And now we have already all terms given, okay? We have all terms given because we know that this term was just our Bernoulli distribution, right? Given theta, the outcome is just a Bernoulli, right? It's theta to the power of tail, which was now our 1, and 1 minus theta to the power of heads, which is 1 minus f, right? By the way, this is a standard trick you might also want to use in the future. So if you use here like this 0, 1 view, you can just use it as an exponent, right? So if this is 1, meaning tail, this term kicks in. If this is 0, meaning head, this becomes 1, and then this term kicks in, right? So because to the power of 0 disappears and to the power of 1 stays. So this is one nice way of writing down a Bernoulli distribution. And this is potentially what you will also encounter later on. Think about it in a bit more detail. These exponents and 0, 1 indicator view helps you to write these distributions in a very compact form. Okay, so back to what we had here, right? We had here this term, which is a Bernoulli, and we had this term, which we just derived in the previous part of the video. This is our posterior distribution over theta, okay? Which is this term here, which we know it's a Bernoulli beta distribution, okay? So we have these two terms, right? So we have this first term, we have the second term, and now again, which we skip here, you can of course now plug it in and you can solve this integral, and this also nicely flows everything together here in this simple case, and it turns out the solution is this here. So it's not too important how this follows. Of course, you feel free to derive it, but it turns out this is the solution, okay? And this again, and this is important to note, this is again now another Bernoulli distribution. Okay, this is a Bernoulli distribution which has two different outcomes, 0 or 1, right? So this can be 0 or 1, as we said. If it's 0, right, note that then this here disappears and this stays and this here, right? And if it's 1, this here becomes 1, this stays, this disappears, and this stays. So if you look at the Bernoulli distribution, you see here we have the parameter for being 1, so it's t plus a. This term divided by the denominator, okay? Very important, and this is often confused, what we have seen so in many exams. So be careful what parameter you're reasoning over. Here you're reasoning about f, and f can be 1 or 0, tail or head, right? 1 or 0. And of course, then the outcome should be a Bernoulli distribution, because Bernoulli distribution is 0 or 1. So this is not a beta distribution. Beta is between 0 or 1, right? An interval, right? So here, this is 0, 1, so this is a Bernoulli distribution, okay? Again, this here is theta, which is living between 0 and 1, so it makes sense to have here beta distribution, okay? Again, be careful what parameter you're reasoning over and what is the domain of this parameter. Here it was 0 or 1, head or tail, okay? So long story short, this posterior predictive distribution turns out to be again a Bernoulli distribution with this specific parameter. Important here is there is no theta anymore, as you see, right? We have integrated out this theta. We have marginalized it out right here. We have marginalized it out, it disappears. So there is no theta. The only point which is left is our prior belief, A and B, and our observed data, T and H. There is no theta anymore. It disappeared because we integrated it out. Okay? So this is called the fully Bayesian approach. And what it intuitively is doing, and this is what you see here, it's not taking a single theta and makes an estimate. So before we took here, for example, theta map and we derived it, or we took theta MLE and we derived this, but we are taking a weighted average over all possible thetas, right? So here, these are the different terms we used so far with theta map and theta MLE, and now we are using different thetas, right? So here, this is 0.1, 0.2, every theta, right? It's integrating over all possible thetas, and the result we are getting here is weighted according to the posterior distribution, okay? So if we scroll back a bit here to these diagrams here, for example, so far in the map solution, we have taken this point here, right? And then we set the next point, the next coin as 0.2 probability to show a tail. What we are doing now is more like we are taking all these different solutions into account, right? And we're taking a weighted average across these, right? So this has a small probability to occur, right? So this theta has a very high probability, so it gets a high weight. These thetas are less likely, so they get a small weight, but everyone is taken into account in a weighted fashion, okay? Everyone is taken into account in a weighted fashion. So this gives different weight to different thetas, and here's the specific outcome we're expecting, okay? Good. And then this essentially summarizes the three different ways we can now do our predictions. We can use the MLE, we can use the map, and we can use the full Bayesian. And in every case, the solution was, of course, a Bernoulli, because it's either head or tail. Here it was a Bernoulli with these parameters, right? The very first one, very intuitive one, right? The ratio of observed tails to all. Then we had our map estimate, where we had here additionally these kind of prior knowledge incorporated, right? With this A -1 and here this -2 term. And then finally, in the fully Bayesian view, we also had a Bernoulli where this was the result. Okay, you see this is extremely similar to this one, but we are missing the -1 and the -2 here. Okay, but this was really properly derived by integrating over all possible thetas according to the posterior distribution. Okay, so this, if possible, of course, is the nicest you can do, right? Because you don't have to derive a theta, you don't have to derive a point estimate, but you're taking all possible thetas according to their importance into account. This is really the actual question we would love to answer, right? What is the next coin flip given the data we have seen so far? But as I said already, in practice, you are always, most of the time, using this because the last one is often intractable to compute. Okay, so here just one more time, a couple of examples. You see essentially that they are quite similar, right? So if you, for example, pick this as a prior, so we believe it's a fair coin, and we have some observations. We see, for example, this is the MLE estimate, the map estimate is a bit larger, and the fully Bayesian is even larger here in this case. And then again, if we get more data, for example, we see that they're all getting more and more similar, right? That's a core idea in general. The more data you have, the more important becomes this likelihood term. And then in both cases here, it essentially becomes less important what the prior belief is, right? So these terms with the A's, they become less and less important. So with many data, MLE, map, and also the fully Bayesian are more or less the same at the end of the day, okay? So the predictions become, the difference in the prediction becomes less noticeable. Okay, so with this, we are at the end of this introduction chapter to probabilistic inference. I know this is a hard topic if you're not too familiar with probabilistic topics in general, right? Like probability theory. Please watch this video a couple of times and ask your questions. But just to wrap up one more time, so what you should use here as a takeaway or learn as a takeaway is we learned the maximum likelihood estimate. This is essentially the parameter vector, the solution of the parameter vector, which maximizes the likelihood function. Data given the parameters. This is what we're maximizing. We had the map, which is looking at the posterior distribution, was a maximum or the mode of the posterior distribution. The posterior itself, right, it's like this posterior proportional to the likelihood times prior, and if we want to have it equal, we have to divide by the evidence. Then we have the fully Bayesian view, which is rather complicated, but the core idea is that we don't want to look at a single parameter estimate, a point estimate, but we want to use a full distribution, and then we can integrate over all these parameters, meaning essentially we take some weighted averaging over all possible parameters. In general, we should know these three terms, right? Prior times likelihood is proportional to the posterior, right? And also what you learned is the Ird assumption. This was essentially the core that we can make at all any statement here, independent, that we can factorize the distribution, identical, that they have all the same parameters, so to say. And finally, you use the concept of conjugate priors to make our life easy, right? If you have a likelihood function and you pick a conjugate prior, then the posterior has the same shape, comes from the same family as a prior. So these are both betas or both Gaussians, for example. And then two other tricks you should remember. One is if you have like a function you want to maximize or minimize, or where you're interested in the critical points, you can also apply a monotonic function, then these critical points don't change. It often makes it easier, specifically in our world. Please do this log transformation, okay, because that's often much better. And lastly, you often actually don't have to solve these integrals because you can do pattern matching. You can see, does it look familiar? Is it a known distribution? And then you don't have to solve it. You can just plug it in. And this is what we specifically use for the beta distribution here. Okay, so with this, we are at the end of this video. I hope you enjoyed this introduction. Ask your questions on Piazza as usual, and we will see us in the next week, where we then use these concepts in an actual machine learning context, where we talk about linear regression, and then in the week after also about linear classification. And then you will see how this all nicely flows together and gives you a very good foundation to understand machine learning from a proper foundational perspective. Thank you, and see you next week.